The air in the Joint Chiefs of Staff conference room was a heavy, static electricity you could almost taste. It clung to the polished mahogany table and the starched uniforms of the men assembled. But it wasn't just the heating unit that made the room oppressive. It was the Sputnik satellite, currently tracing its invisible arc thousands of miles above them. Just 6 days earlier, the Soviets had launched it, and now, that incessant, demoralizing beep, beep, beep was the soundtrack to every high-level defense meeting. Admiral Arleigh Burke, Chief of Naval Operations, gripped a coffee cup hard enough to crack the porcelain. His eyes, usually sharp and penetrating, were currently glued to a large, topographic projection map of the globe. The map was mostly empty, a vast, hostile emptiness. "Gentlemen," he said, his voice a low, gravelly rumble, "the enemy now has the capability to hit us from space. They have demonstrated the range, and they have demonstrated the accuracy. The beep is just the opening bell." General Thomas S. Power, Commander-in-Chief of the Strategic Air Command, a man known for his grim, unshakable focus, leaned forward. His face was a mask of cold fury. "Admiral, with all respect, Sputnik itself isn't the threat. It's the Intercontinental Ballistic Missile, the ICBM, that put it up there. It means any city, any base, any command center on this continent is, at best, a 30-minute target. We're blind. Plain and simple. Our DW line, our distant early warning chain across the Arctic, it gives us minutes, not the hours we need for a strategic response. We can see a bomber, sure, but a missile? Once it clears the horizon, we are effectively deaf, dumb, and waiting for the punch." He pointed a thick finger at the map, tracing a line from the Soviet interior over the Arctic and down toward the American Midwest. The Earth, with its cruel curvature, was their enemy's most effective weapon. It created an invisible wall for conventional microwave radar. The radar waves, traveling in a straight line, simply shot off into space, uselessly tracking nothing but atmospheric noise once they passed the tangent point of the horizon, usually only about 200 miles out. 200 miles in the age of propeller bombers was manageable. 200 miles in the age of the ICBM was a death sentence. A young, civilian physicist, Dr. William J. Thaler, sat quietly at the back of the room. He wore a slightly rumpled suit that stood out starkly against the crisp, starched uniforms. He was a relative newcomer to the Office of Naval Research, ONR, but he wasn't new to unorthodox ideas. He had been invited by a lower-ranking aide, an afterthought who thought the Joint Chiefs might benefit from a wild card. Thaler, a man who had earned his Ph.D. in physics from Catholic University, wasn't a military contractor, an aerospace executive, or an aging wartime prodigy. He was an academic with a fascination for the obscure behavior of radio waves. He had spent the last several years obsessed with a forgotten piece of physics, the ionosphere. The ionosphere, a layer of the Earth's upper atmosphere, roughly 30 to 600 miles up, ionized by solar and cosmic radiation, was primarily known to the public as the reason you could pick up distant shortwave radio stations at night. It acted like a giant, natural mirror for certain high-frequency, HF, radio signals, bouncing them back toward Earth. Radio engineers called this skywave, or skip. It was a nuisance to stable communications, but to Thaler, it wasn't a nuisance. It was a secret passage. General Power slammed his fist lightly on the table, the sound echoing in the sudden silence. "We need a system that can see a launch within the first 5 minutes. We need to see them thousands of miles away while they're still over their own territory. We need to see over the horizon. And frankly, gentlemen, that technology doesn't exist. We're pouring billions into satellites, but that's a decade away from a fully operational system. What do we do in the meantime?" Thaler finally spoke, his voice clear but slightly tentative against the backdrop of brass and steel. "General, with all respect, I believe the technology does exist. It's been in plain sight for 50 years. Every eye in the room swiveled to him." Burke raised an eyebrow, a gesture that spoke volumes. Thaler didn't flinch. He walked to the projection screen, picked up a chalk from the tray, and drew a simple, yet profoundly revolutionary, diagram. He drew a line representing the Earth's surface. He drew a missile arcing up from a point in the Soviet Union. And then he drew a conventional radar beam shooting out from the U.S., stopping abruptly at the horizon. Our current radar, using microwaves, is line of sight, he explained, tapping the line that disappeared into space. But if we change the frequency, if we switch from microwaves to high-frequency, HF, radio waves, something extraordinary happens. Those HF waves are not stopped by the horizon. He drew a second line, originating from the same point in the U.S., but this one arced upward, reflecting sharply off an invisible ceiling he labeled ionosphere, and then came plunging back down hundreds or thousands of miles away, landing precisely where the missile was ascending. Instead of seeing over the hill, gentlemen, Thaler declared, turning to face the stunned Joint Chiefs, we can skip the signal off the sky. The ionosphere is the mirror. We don't need a satellite to see thousands of miles into the Soviet interior. We just need to stop fighting the Earth's curvature and start using it. We use the same skywave that lets a kid in Des Moines pick up a radio broadcast from London. We could track ICBMs with it. We can track bombers with it. We can see over the horizon. The silence that followed was even heavier than the pre-Sputnik tension. A civilian, a physicist whose work was mostly theoretical, was proposing to turn a simple radio quirk into the continent's first line of defense against nuclear annihilation. It sounded utterly mad, a desperate last-ditch attempt to outwit physics itself. It sounded like a trick, a crazy radar trick. The assembled leadership didn't burst into laughter, which Dr. William Thaler considered a small victory. Instead, they offered the kind of skeptical silence only men holding the ultimate responsibility for national security could manage. Admiral Burke finally leaned back, the coffee cup now resting on a coaster. His gaze was steady, evaluating. Dr. Thaler, Burke began, the title delivered with the precise neutrality of a judge addressing a highly unusual defendant. You are suggesting that the same atmospheric phenomenon that allows a ham radio enthusiast in Kansas to talk to someone in Australia, a phenomenon that is notoriously unstable, depending on the time of day, season, and solar weather, could be reliably harnessed to detect a $20 \text megaton warhead entering our airspace. Is that correct? Thaler nodded. Not just reliably, Admiral, but predictably. We've spent decades trying to eliminate the ionosphere from our communications. We've considered it noise, a source of fading and distortion. But we haven't tried to use it as a component of a radar system. Think of a conventional radar pulse. It's a precisely timed, high-power burst of energy. Now, imagine that pulse, but using the high-frequency, HF, band, what people call shortwave. We beam it up at a shallow angle. It hits the F layer of the ionosphere, where the highest concentration of free electrons exists, and that layer acts as a curved lens or a mirror, sending the energy back down hundreds or even thousands of miles beyond the visible horizon. General Power was less patient than the Admiral. And what happens when it hits a missile, Doctor? It just bounces back to us over the same unstable path. How do you distinguish a Russian ICBM from a tropical thunderstorm? Or, God forbid, solar flare interference? Our current radar relies on a precise, direct return path. Yours is a game of atmospheric pool. Thaler walked back to the drawing and used the chalk to refine his sketch, adding small details that began to shift the perception from a wild guess to an educated gamble. General, that's where the Doppler shift comes in. A missile is moving at high velocity. The radar wave that hits it will have its frequency slightly altered by that speed. That's the Doppler effect. The ionosphere might be noisy, but it's mostly stationary relative to the ground. A missile is moving at thousands of miles per hour. The Doppler signature of a speeding missile, even a faint one, will stand out dramatically from the static of the ionosphere or a non-moving target like the sea or land. He pointed to the theoretical impact zone thousands of miles away. We look for a distinctive moving target signature. We're not simply trying to detect a faint reflection. We're trying to detect a moving reflection, a shift in frequency that can only be caused by something accelerating at hypersonic speed. The ionosphere gives us the range, The Doppler gives us the target discrimination. The core of Thaler's vision was the revolutionary shift in military perspective. For 20 years, since the first radars of World War II, the goal had been to go above the short-wave bands, into the microwaves, because those straight-line signals offered the best resolution and were the most stable. Now, Thaler was proposing a strategic retreat back into the noisy, messy world of short-wave radio, not for stability, but for reach. The enemy was no longer the fighter plane at 100 miles. The enemy was the ballistic missile at 3,000 miles. Range trumped resolution. You're talking about using shortwave radio to track a nuclear missile, commented Dr. Herbert York, the director of Defense Research and Engineering, who had been silent up until this point, weighing the technical absurdity against the strategic necessity. That's what they call junk frequency. The energy requirements alone would be staggering to get a detectable return from that distance. Thaler conceded the point smoothly. The power demands are high, Dr. York. We'd need massive antenna arrays, hundreds of acres, perhaps, to focus the beam with enough energy. And we need sophisticated signal processing to filter out the noise. We wouldn't be using a typical pulsed radar, but something more continuous, more integrated with computational power. This isn't just a bigger radar. It's a completely new philosophy of detection, based on exploiting a previously discarded natural phenomenon. He knew the true battle was not with physics, but with bureaucracy and disbelief. He wasn't proposing an upgrade. He was proposing a paradigm shift. He needed a champion. He needed someone with enough authority to grant him the resources to build a system that sounded less like a weapon and more like a parlor trick. Admiral Burke stared at the sketch on the map, the sweeping arc of the radar beam, bending across the curvature of the planet. It was a beautiful, elegant solution to the ugliest of problems. It was exactly the kind of outside-the-box thinking the nuclear age demanded. He looked at General Power, who was still skeptical but clearly intrigued by the possibility of seeing Russian territory. The strategic value was undeniable. If it worked, they would have hours, not minutes, to respond to a launch. Burke picked up the phone. "Get me the Secretary of Defense," he instructed his aide, never taking his eyes off Thaler. "Dr. Thaler, you've presented a theory. Now let's talk about a project. You'll need resources, money, and men. But more than that, you'll need speed. The clock is ticking, and that beep from orbit is only getting louder." The room had tilted. The crazy trick was now an official, top-secret U.S. Navy research program. The name of the project would be suitably dry to conceal its radical nature. Project TP, short for Thaler's Project. The transition from a theoretical sketch on a blackboard to a funded, black-budget program was dizzying, a characteristic rush of Cold War panic overriding standard bureaucratic caution. Project TP was officially sanctioned in the tumultuous months following the Sputnik shock. William Thaler, the civilian physicist, suddenly found himself the unlikely ringmaster of a high-stakes military experiment. His lab wasn't a neat, academic office. It was a sprawling, top-secret installation near Chesapeake Bay, Maryland, with a Naval Research Laboratory, NRL, could provide the necessary technical muscle and secrecy. Thaler's team was a curious mix of academics, Navy radio men, and engineers with an affinity for the bizarre. He deliberately sought out those who understood the messy side of radio, the ham operators and the old-school pioneers who hadn't forgotten the ionosphere's power when the world had shifted its focus entirely to high-frequency, line-of-sight communications. They were the ones who knew how to work the skip. The fundamental challenge wasn't proving that radio waves could bounce off the ionosphere. That was physics fact. The challenge was proving they could do so with enough power, stability, and signal integrity to detect a target the size of a missile warhead thousands of miles away, moving against a backdrop of natural radio interference. The first crucial step was designing the antenna array. To focus the high-frequency, HF, radio energy with enough precision for a useful radar return, Thaler needed an aperture far larger than any standard Navy radar dish. He couldn't use a rotating dish. He needed a fixed wall of metal oriented to beam the signal low toward the horizon, banking it off the ionosphere. The result was the construction of a massive, seemingly crude, log-periodic antenna array. Hundreds of wires strung between tall wooden poles, stretching across acres of protected military land. It looked less like a cutting-edge military device and more like a colossal, metallic cobweb designed by a mad scientist. This antenna array would generate the sheer power needed. Normal short-wave radio transmitters operated on a few hundred or thousand watts. Thaler's system, however, demanded transmitters capable of blasting signals up to the megawatt level. Raw energy orders of magnitude greater than standard broadcasting, necessary to ensure a tiny fraction of the signal survive the double journey. Up to the ionosphere, down to the target, back up to the ionosphere, and finally, back to the receiving array. But power alone was insufficient. The primary obstacle, as General Power had pointed out, was noise. The shortwave band was perpetually congested. Broadcasts from foreign nations, atmospheric static from lightning, the aurora borealis, and the constant, fluctuating interference from the sun itself. To detect the almost imperceptible Doppler shift caused by an ICBM launch, they needed a way to pull that faint, moving signal out of a blizzard of static. This required a complete rethinking of signal processing. Conventional radar relied on short, powerful pulses. Thaler's over-the-horizon, ODH, concept required a much slower, more continuous signal that allowed computers, rudimentary as they were in the late 1950s, to perform complex analysis. They introduced advanced matched filtering techniques, mathematical algorithms designed to recognize the specific frequency pattern they sent out, and more importantly, to instantly detect any tiny shift in that frequency that indicated movement. The computer wasn't just looking for a blip, it was listening for a whistle. Thaler faced constant internal resistance. Many established scientists at the NRL viewed Project TP as a diversion, a technological sideshow. Their eyes were on space-based surveillance, the long-term, elegant solution. Thaler was working in the mud, stringing wires, fighting atmospheric physics, and demanding computer power for a radio band everyone else had discarded. He was told repeatedly that the ionosphere was too capricious, too unreliable for the kind of consistent, 24/7 detection the military required. Thaler countered this skepticism by emphasizing the inherent advantages. Satellites were expensive, vulnerable, and years away. OTH radar, if successful, could be deployed rapidly and affordably. Furthermore, because the signal arrived back at the radar site from above, it was uniquely immune to low-level electronic countermeasures that could confuse conventional line-of-sight radar. He didn't just need to prove the physics. He needed to prove the system stability. They spent countless hours mapping the ionosphere's behavior, learning its daily and seasonal rhythms, how the D, E, and F layers of ionization rose and fell, how the position of the optimal skip zone shifted hundreds of miles with the rotation of the Earth. Thaler's team became less like radar specialists and more like high-altitude meteorologists, predicting the conditions of the natural mirror they intended to use. The pressure from Washington was immense. Every new Soviet missile test, every report of advanced bomber deployment, ratcheted up the urgency. Thaler knew his team wasn't just building a radar. They were building the American continent's only immediate hope for a truly extended warning system. The goal was simple, terrifyingly so, to detect the launch of a missile from deep within the Soviet Union and provide a minimum of 3 hours of warning, enough time for SAC bombers to take off and reach fail-safe positions. Failure meant mutual destruction. The Maryland facility hosting Project TP in the late 1950s felt less like a futuristic defense complex and more like a high-voltage power station grafted onto a sprawling farm. The massive log-periodic array stretched for nearly a mile, an imposing, geometric forest of wires that hummed with latent energy. This was the transmitter, a second, equally vast array, positioned many miles away, acted as the receiver, listening for the faintest echoes. The heart of the operation was the concrete bunker housing the transmitters and the early computing equipment, a room that smelled of ozone, hot vacuum tubes, and stale coffee. Dr. Thaler stood before the main console, a labyrinth of dials and monochrome screens, watching the readouts of the transmitted power. They were preparing for their first real-world, long-distance trial, an intentional attempt to use the ionosphere's F-layer to bounce a signal into a predetermined skip zone in the Atlantic Ocean, thousands of miles away, and receive its reflection. The signal was a specially coded, continuous wave, designed not just to be powerful, but to have a long integration time. The duration the computer had to listen and average the returns, effectively pulling the signal out of the noise. "Ready to go, Doctor," confirmed Lieutenant Commander Evans, a grizzled Navy radio man responsible for the transmission gear. "Putting 3 megawatts into the array. She's humming like a hive of bees." Thaler gave the nod. The signal blasted out, a massive burst of high-frequency, HF, energy, surging skyward. On the receiver displays, the expected result was chaos. The screen immediately lit up with a blinding array of noise, known technically as clutter. There were returns from local terrain, atmospheric discharges, and the constant din of international shortwave traffic. Thaler's challenge wasn't just finding a needle in a haystack. It was teaching the haystack to identify a very specific type of needle. The initial results were demoralizing. The ionosphere, their essential mirror, was proving to be a temperamental partner. The HF signal, instead of cleanly reflecting, was often scattered, absorbed, or smeared. The layer of free electrons in the F layer was constantly undulating, like a wavy pane of glass. This caused the returning echoes to suffer from severe Doppler spread, meaning the faint, vital frequency shift caused by a moving target would be swallowed up by the seemingly random movement of the ionospheric layer itself. "The mirror is shaking, Doctor," observed Dr. Chun, the lead signal processing specialist, tapping a complex waveform display. "Look at the frequency shift keying, FSK, response. The return from a sea surface at 2,000 miles is supposed to be steady, reflecting the zero velocity target. Instead, it's broadened, smeared across multiple hertz. If the water looks like it's moving at 50 knots, how will we isolate an ICBM moving at 20 times the speed of sound?" This was the core technical hurdle. Standard radar worked by measuring the time a pulse took to travel to the target and back. Project TP couldn't do that accurately because the skip path varied minute by minute. It had to rely almost entirely on the Doppler signature. If the atmosphere's inherent movement masked the target's movement, the system was useless. Thaler paced, hands clasped behind his back, staring at the incomprehensible white noise. "We need to calibrate the ionosphere itself, Chun. We can't eliminate the noise, but we can measure its character. We need a real-time system to analyze the non-moving returns, the clutter from the sea, land, and the ionosphere itself, and subtract that background noise dynamically. We need to create an atmospheric baseline." The team spent the next year not looking for targets, but looking for stability. They began transmitting continuous reference signals, like sonar pings into the atmosphere, to constantly measure the ionosphere's height, density, and movement. They integrated the new data into the computational system, effectively teaching the computer to filter out the shake of the mirror. This real-time ionospheric sounding was a revolutionary step, turning the biggest weakness of OTH radar into a critical component of its operation. One freezing night, months into the testing, the monitor displaying the long-range Doppler analysis suddenly registered a clean, high-velocity signature. It was a strong, undeniable return with a frequency shift consistent with a target moving toward them at supersonic speed, thousands of miles out in the skip zone. The bunker instantly went silent. Thaler rushed to the console, his heart hammering against his ribs. The reading was sustained for nearly 2 minutes. Could it be? A rogue Soviet submarine-launched missile test? A bomber? Chun frantically checked the signal characteristics. "It's too clean, Doctor," he finally announced, his voice tight. "The frequency shift is almost too perfect for a real-world moving object, and the location correlation is weak." They eventually determined the source. An unusual, temporary sporadic E-layer formation in the atmosphere had created a perfect duct for a massive, commercial short-wave broadcast from Europe. The sheer power of the broadcast, combined with the atmospheric ducting, had mimicked a clean, high-velocity Doppler shift. It was a terrifying false positive. The risk of crying wolf, especially a nuclear wolf, was unacceptable. Thaler realized the stakes had just doubled. It wasn't enough to see something over the horizon. They had to be absolutely certain of what they were seeing. Their algorithms had to evolve beyond mere detection to sophisticated classification. They needed to develop the fingerprint of a missile launch, and they needed to see one to establish that baseline. The European broadcast scare had been a brutal, indispensable lesson. The system could see over the horizon, yes, but its vision was blurred by atmospheric noise, forcing Thaler to confront the most difficult element of Project TP, target classification. If the ODH radar was to be a credible weapon, it couldn't just find movement. It had to positively identify the unique signature of a massive, accelerating rocket. They needed to see a missile launch, a real one, and analyze its Doppler return to build the necessary filter. Thaler immediately petitioned the Navy and the newly formed NASA for access to their launch schedules. He needed a cooperative target, an American ICBM, or Intermediate Range Ballistic Missile, ARBM, test fired from Cape Canaveral, Florida, into the Atlantic Missile Range. Tracking a domestic launch, thousands of miles away from the Maryland receiver, would provide the perfect environment for calibration without the ambiguity of natural interference or the threat of Soviet retaliation. This was the only way to build the nuclear wolf fingerprint they desperately required. The key to Thaler's detection strategy wasn't the missile body itself. A ballistic missile, even an Atlas or a Titan, was a relatively small, radar-absorbing metallic object, difficult enough to see with line-of-sight radar, let alone after a 4,000-mile atmospheric skip. The true target, Thaler hypothesized, was the exhaust plume. When an ICBM launched, its engines incinerated thousands of pounds of propellant per second, creating a colossal, intensely hot cloud of combustion products and unburnt fuel. Crucially, the extreme heat and chemical reactions in the exhaust ionized the surrounding air, creating a massive, electrically charged cloud, a perfect, dense reflector of the HF radio waves used by Project TP. Thaler explained the concept to his skeptical military overseers. Gentlemen, we're not tracking the bullet, we're tracking the smoke trail. The missile body is small and stealthy. The plume is a gigantic, intensely moving plasma reflector that grows larger the longer the engine fires. It is, for our purposes, a perfect high-velocity target. The size of this ionized cloud, extending hundreds of feet behind the rocket, provided the large reflecting surface they needed to overcome the vast distance and atmospheric losses. This insight fundamentally changed their algorithmic approach. They were now looking for a multi-phase Doppler signature, a low-speed signature on the ground, followed by a rapid, clean acceleration profile, the burn phase, and then a distinct, slightly quieter, but still moving signature as the plume dissipated and the missile coasted toward its apogee. This entire profile, unique to an ICBM launch, would be the required classification fingerprint. In the spring of 1958, Thaler received the green light. Project TP was authorized to track an upcoming test of an Atlas ICBM from Cape Canaveral. The anticipation in the Maryland bunker was palpable. For months, they had only chased atmospheric ghosts. Now they were chasing a $50 million rocket hurtling into the sky. The day of the launch arrived. Thaler, standing beside the massive processing cabinets, felt the tension that comes from knowing years of work rested on a single 10-minute event. The coordination was complex. Cape Canaveral transmitted the exact time of liftoff and the intended trajectory data via secure link, allowing Thaler's team to tune their receiver array precisely to the expected skip zone over the Atlantic. T-minus 10 seconds to liftoff, crackled the voice from the speaker. The team watched the console, its screen still dominated by the flickering, static white noise of the ambient atmosphere. The megawatt transmitter was already saturating the ionosphere with the probing HF signal, waiting for the echo. T-minus 0. We have ignition. Thaler focused on the Doppler processing screen, the one designed to filter out the noise and display only the clean, high-velocity returns. For the first 30 seconds, there was nothing new, just the expected atmospheric clutter. Doubt, a constant companion in the world of experimental physics, crept into the room. Had the ionosphere scattered the signal too much? Had the plume failed to reflect the HF waves as theorized? Then, 60 seconds after liftoff, a distinct, clean, and unmistakable bright line appeared on the spectrum analyzer, rising rapidly from the baseline. It wasn't the fuzzy blur of the European broadcast. It was sharp, intensely focused, and its frequency shift corresponded exactly to the accelerating speed of the Atlas missile as reported by the ground radar at the Cape. "We have it!" yelled Dr. Chun, his voice hoarse with exhilaration. "Doppler shift is clean. Tracking the plume. Look at the intensity. It's immense." For the next 4 minutes, as the Atlas roared upward and the plume grew to its maximum size, Project Teepee tracked it perfectly, thousands of miles away. The signature precisely matched the calculated trajectory, giving them undeniable proof that their crazy radar trick worked. They weren't just seeing a reflection. They were tracking a nuclear-capable vehicle in real time, over the horizon, using the atmosphere as their lens. The invisible wall was broken. The strategic balance of power, at least in the critical sphere of early warning, had just tilted back toward the United States. The successful tracking of the Atlas launch was the turning point for Project Teepee. Dr. Thaler and his team had empirical proof, captured on reels of magnetic tape and stacks of printouts, that the theory of over-the-horizon, ODH, radar using ionospheric scatter was not just feasible, but dramatically effective. The data provided an exquisite, detailed Doppler fingerprint, the characteristic acceleration curve of a boosting ICBM, clearly distinguishable from any other atmospheric or man-made interference they had yet recorded. Thaler immediately presented the results to the Joint Chiefs of Staff and the Secretary of Defense. This time, the atmosphere in the Pentagon conference room was drastically different. The cold skepticism that had greeted him 18 months earlier was replaced by a tense, focused awe. He didn't draw diagrams. He played the tapes. "Gentlemen, this is the raw data collected from our receiver array in Maryland, simultaneously with the official Cape Canaveral tracking reports," Thaler explained, displaying 2 synchronized graphs. One showed the speed and trajectory as measured by the conventional, line-of-sight radar systems at the launch site. The other showed the speed and trajectory derived from the Doppler shift detected by Project Teepee, thousands of miles away, relying solely on the reflected signal from the ionosphere. The 2 lines were almost perfectly congruent. General Power, the most vehement skeptic initially, leaned over the data with the intensity of a man who has just seen an enemy vulnerability exposed. "This is a 4-minute window, Doctor. For minutes of burn time. Does your system continue tracking after the engine cuts off?" Thaler nodded. "Once the main engine cuts off, the large, ionized plume dissipates. The Doppler signature becomes fainter, reflecting only off the smaller missile body. But crucial information has already been extracted. We have established the launch location with reasonable accuracy and, most importantly, the initial trajectory and velocity vector. This allows us to predict the likely impact zone with sufficient precision to trigger a defensive alert and launch countermeasures, all while the Soviet missile is still barely 20 minutes into its 30-minute flight." The strategic implication was staggering. The DW line offered maybe 10 to 15 minutes of warning against a missile approaching North America. Project Teepee offered potentially hours of warning about a missile launching from inside the Soviet Union. It completely shifted the temporal balance of the Cold War. Despite the compelling evidence, the scientific community, particularly those invested in the decade-long push toward microwave technology and satellite surveillance, remained hesitant. They argued that the successful Atlas test occurred under optimal conditions. The precise frequency was chosen, the ionosphere was stable, and the target's trajectory was known in advance. They maintained that relying on the constantly fluctuating ionosphere for continuous, 24/7 surveillance across the vast Soviet landmass was too great a gamble. The system would inevitably be blinded by severe solar flare or seasonal ionospheric variations. Thaler had anticipated this. He revealed the second phase of their research, the development of frequency diversity and adaptive signal selection. "We are not fixed on one frequency," Thaler stated. "The system operates by constantly sounding multiple adjacent HF bands. If the primary frequency, say 15$/text megahertz, proves to be poorly reflected due to ionospheric conditions, the system immediately shifts to the next best frequency, perhaps $10$/text megahertz or $20$/text megahertz. Our antenna arrays are designed to operate across a very wide bandwidth. We don't just rely on the ionosphere. We track its condition in real time, and we adapt the radar's operating frequency to match the current atmospheric optimum. This effectively mitigates the issue of unpredictability." The concept of a radar system that continuously listened to the environment and tuned itself accordingly was a huge leap in engineering. It was the antithesis of the stable, fixed-frequency radar systems the defense industry was accustomed to. This adaptive ability silenced the majority of the technical skeptics. The Department of Defense, recognizing the immediate and desperate need for an early warning system that could bridge the gap before operational surveillance satellites were feasible, moved quickly. Project Teepee was to be dramatically expanded. The successful trial became the catalyst for the development of a full-scale, operational OTH radar network. The immediate next step would be moving beyond the controlled environment of the American coast. Thaler was tasked with designing a system capable of looking directly into the Eurasian heartland, the true strategic zone. The experimental setup in Maryland was insufficient for this task. They needed a dedicated site with massive power generation and antenna footprint, strategically located to exploit the optimal skip angles for looking across the entire Atlantic and into the Soviet sphere. The success of the Atlas tracking had simply paved the way for the real, infinitely more complex operational mission. The mandate from Washington was stark: go operational and go fast. The successful but limited Maryland array could only see so far into the Atlantic. To peer into the Soviet heartland, specifically the vast, empty plains where missile complexes were believed to be hidden, Dr. Thaler required a geographical advantage. The beam needed to be launched from a location that minimized atmospheric distortion near the source and provided the best possible angle for the ionospheric bounce to land squarely over western and central Eurasia. The chosen location was remote, a massive, sparsely populated coastal region in Maine, selected for its unobstructed view of the Atlantic and its proximity to the necessary high-latitude ionospheric reflection points. The operation was classified top secret, designated a high-powered communications research facility to disguise its true purpose, detecting the Doppler signature of nuclear doom thousands of miles away. Thaler's role shifted drastically from physicist to logistical orchestrator. He was no longer dealing with equations. He was dealing with concrete, copper, and megawatts. The sheer scale of the new facility dwarfed the original test site. The Maryland array was a prototype. This was a weapon system. It required an antenna farm that stretched for miles, not hundreds of poles, but thousands, supporting a colossal web of transmission lines designed to handle continuous megawatt output. Contractors were flown in under intense security clearances, tasked with building a fortress of science in a wilderness. The engineering challenge was immense, particularly concerning the transmitter facility. Pushing high-frequency radio waves at $5/text megawatts, or more, 24 hours a day, demanded industrial-scale power generation and cooling systems. The vacuum tubes that generated this immense energy glowed with blistering heat. Thaler oversaw the construction of a dedicated power plant just to run the radar, with massive water cooling tanks necessary to keep the fragile electronics from melting down under the continuous, high-duty cycle operation. The facility had to be a fusion of a power station and a supercomputer center, all wrapped in a Cold War cloak of secrecy. Signal reception presented its own unique problems at this operational scale. The receiver site, placed hundreds of miles from the powerful transmitter to prevent interference, was a marvel of acoustic and electronic isolation. The faint returning echo, after its journey to the ionosphere, to the target, and back, was often measured in nanowatts, a whisper against the roar of atmospheric static. The receiving antennas needed to be even more extensive and sensitive than the transmitters, covering an even larger area to maximize the collection aperture. Thaler brought in a new team of dedicated computer engineers to tackle the real-time adaptive processing. The Atlas test had proven the concept, but the system had to be fully automated. The computer had to constantly monitor the ionosphere, using the system they had developed, real-time ionospheric sounding, predict the optimal HF frequency path, tune the transmitter, and then, most crucially, perform the complex mathematical filtering, the matched filtering and clutter subtraction, all within seconds. This was 1959. Computer systems were vast, magnetic core behemoths that filled entire temperature-controlled rooms. Thaler's operational system needed the computing power equivalent to hundreds of conventional business machines just to manage the filtering. It was a race to push the limits of early solid-state electronics and programming to make the complex atmospheric calculations instantaneously. One of the project lead engineers, Robert Buzz Alden, a former Bell Lab specialist, summarized the feeling. Dr. Thaler asked us to build a brain for a radio. But the radio is 3 miles wide, and the brain has to think fast enough to tell us if Russia is attacking before the missile has even left their airspace. We are fighting noise on the surface of the sun and the limitations of 1950s technology simultaneously. The logistics of supplying the remote site, securing the classified equipment, and maintaining secrecy from the local population created a constant, low-grade tension. The project was consuming money and resources at an alarming rate, and every dollar spent demanded a demonstrable return. The political clock was ticking. The Soviets were continuing to test and refine their ICBM capability, and the intelligence consensus was that a fully operational Soviet arsenal was imminent. Thaler spent months shuttling between Washington, checking funding and security clearance, and the muddy construction site in Maine, ensuring that the sheer scale of the antennas translated into the necessary geometric precision. This massive, half-finished monument to desperation and genius was their only shield. It was the physical manifestation of the over-the-horizon concept, a machine built to cheat the curvature of the Earth, and by America, the most precious commodity of the nuclear age, time. By the beginning of 1960, the massive main facility, codenamed Cobra, was humming. The vast antenna arrays, stretching like the ribs of a gigantic, grounded skeleton, were energized. Inside the primary operations bunker, the air-conditioned rooms housed the roaring transmitters and the blinking, magnetic core memory of the new computer system, nicknamed Guardian. Dr. Thaler and his team were ready to attempt what had, just 3 years prior, been dismissed as fantasy, scanning the inner expanse of the Soviet Union for the first glint of a rocket plume. The operational parameters were exponentially more complex than the controlled test off Cape Canaveral. They were not looking at a known, single target. They were scanning a 90-degree sector spanning thousands of miles of hostile territory, from the Barents Sea down toward the Black Sea. This required constant adjustment of the beam steering. The sheer electrical power and antenna phasing necessary to electronically sweep the HF beam across the skip zone, without physically moving the massive antenna arrays, was a feat of electrical engineering. They were essentially creating a gigantic, invisible fan of radio energy. The initial task was to establish a stable, continuous clutter map of Eurasia. The noise from a 1,000-mile-wide target zone was immense. Mountain ranges, vast flat plains, cities, and the persistent presence of Soviet shortwave broadcasting, all sending back returns that dwarfed the faintest missile echo. Guardian had to learn to recognize, categorize, and filter out every non-moving element on the continent. Thaler's team spent weeks tuning the adaptive filtering algorithms, training the computer to hear the difference between the stationary reflection from the Ural Mountains and the dynamic, rapidly accelerating frequency shift of a missile plume. One persistent, early challenge was polar cap absorption, PCA. The desired path for the radar signal often tracked near the Earth's magnetic poles. During periods of high solar activity, the ionosphere over the poles became so heavily ionized that it absorbed the HF radio waves entirely, creating a massive, unpredictable blackout zone. This confirmed the skeptics' fear. The OTH system was vulnerable to the sun. Thaler immediately authorized a dedicated subproject to develop real-time solar monitoring and prediction models. They began working closely with astronomers and space weather experts, integrating solar flare warnings directly into the radar's operational algorithm. If a major solar event was predicted, the ODH system would either focus on a slightly lower latitude skip path or, in extreme cases, acknowledge a temporary but predictable loss of coverage. They learned to live with and anticipate the sun's temperament, proving that vulnerability could be managed. One cold morning in the late spring, the control room was quiet, lit only by the green glow of the consoles. The operator responsible for the Far Eastern skip zone suddenly shouted, "Doctor, I have something. High velocity, not noise. Consistent Doppler signature, accelerating $3,200 / text miles dollar out. Bearing 270 relative to the array." Thaler moved instantly to the console, heart hammering. The display showed a clean, unmistakable signature, the rapidly rising frequency shift they had seen in the Atlas test. The acceleration profile was identical to an ICBM launch. The speed was accelerating through Mach 5. "Check the solar data," Thaler commanded. "Check the internal systems. Any sign of internal noise or spurious oscillation." Everything was clean. The solar background was stable. The ionospheric sounding showed optimal reflection conditions. This was not a false positive. This was real. The estimated launch location, triangulated by the return time and the beam steering angle, placed the origin deep within the Tyuratam missile test range, the Soviet Union's main ICBM launch facility. "Contact the Pentagon. Priority flash," Thaler ordered, his voice steady despite the seismic implications of the data. "Report. Positive ICBM launch signature detected. Estimated flight time and trajectory to follow." The team held its breath, tracking the signature for the critical 4 minutes of the boost phase, obtaining the launch vector, velocity, and cutoff point. When the engine cut off and the plasma plume dissipated, the signal faded, but the information was recorded and analyzed. Thaler stood there, the weight of the realization settling on him. They had just done it. They had tracked a live, operational Soviet ICBM test, providing a tactical warning that would have been impossible just months earlier. The over-the-horizon radar, Thaler's crazy trick, was no longer an experiment. It was the eyes of America, seen for the first time across the curvature of the Earth, right into the enemy's den. The clock for strategic response had been pushed back from minutes to hours. The confirmation of Project TP's success, the indisputable tracking of a Soviet ICBM test launch from Tyuratam, sent tremors through the highest levels of the U.S. military and intelligence community. The data, meticulously cross-referenced with subsequent intelligence reports that confirmed the date, time, and general trajectory of the Soviet test, provided definitive proof of the ODH system's capability. Dr. Thaler was immediately summoned back to Washington, the unassuming civilian now treated with the reverence usually reserved for wartime heroes. The key takeaway wasn't just detection, but the duration of the warning. Conventional radar would have spotted this missile only as it approached North American airspace. Project TP offered notice while the missile was still climbing over Soviet territory. This extended warning time, measured in hours rather than minutes, completely altered the calculus of strategic deterrence. The U.S. military now had the operational time necessary to execute a controlled fail-safe response, launching Strategic Air Command, SAC, bombers, scrambling interceptors, and placing missile defenses on high alert, eliminating the immediate, use it or lose it pressure that the missile gap had created. This new capability was immediately classified at the highest levels. The Soviet Union could not be allowed to know that its primary strategic advantage, the element of surprise enabled by the Earth's curvature, had been neutralized. The operational system in Maine, codenamed Cobra, became a phantom eye working in total secrecy. The official cover story about a high-powered communications research facility was rigidly maintained, diverting attention from the massive antenna arrays and the constant, subtle humming of the transmitters. However, the internal debate within the Pentagon intensified. While the operational commanders, especially those in SAC, hailed the ODH radar as a vital shield, the scientific and research branches were divided. Many argued that the long-term future lay entirely with space-based DSP, Defense Support Program, satellites, which used infrared sensors to detect the heat of a rocket plume and were immune to the ionosphere's vagaries. They saw Thaler's ground-based HF system as an expensive, temporary solution, dependent on archaic radio frequencies. Thaler countered these arguments by emphasizing redundancy and survivability. A satellite, gentlemen, he argued, is a single point of failure. It can be shot down, jammed, or blinded by a sophisticated adversary. The HF radar is ground-based, hardened, and spread across vast antenna arrays. It is inherently resilient. More importantly, it provides overlap. If a solar flare temporarily blinds a certain satellite path, the ODH radar can adapt its frequency and compensate. Our security cannot rely on a single type of sensor. The ultimate victory for Thaler's concept was the official authorization for a full-scale ODH deployment program. Recognizing the immense sweep required to cover not just the Soviet Union, but also the maritime approaches and other potential launch zones, the military planned for multiple ODH installations across the United States. This expansion was a direct acknowledgement that Thaler's crazy trick was now a cornerstone of continental defense. The success also spurred immediate Soviet curiosity. While they didn't know the specifics of the ODH system, their own intelligence certainly noticed the sudden, massive construction projects in remote coastal regions of the U.S. Furthermore, the immense amount of high-power, continuous HF radio energy being pumped into the ionosphere was detectable by anyone with a sensitive receiver. To the rest of the world, especially amateur radio operators, the powerful, sweeping transmissions sounded like a massive, unintelligible roar, a constant source of interference that clogged the shortwave bands. This accidental but constant radio pollution was Thaler's necessary evil. To see thousands of miles away, he had to shout across the world's natural airwaves. The signal, which looked like noise to everyone else, was the silent guardian, constantly probing the sky and waiting for the telltale, accelerating whisper of Soviet launch. The system was effective, but its very operation created a detectable global signature, a challenge that would define the next generation of ODH development. The operational success of the main ODH radar, designated by a broader military classification, soon became an open secret among the world's most dedicated shortwave listeners and international communication agencies. While the official purpose was obscured, the sheer power and unique signature of the signal, a constant wideband, high-power hum that swept across the entire high-frequency HF band, was impossible to hide. This massive electromagnetic footprint caused significant interference globally, drowning out legitimate radio broadcasts, ship-to-shore communications, and critical amateur radio operations. Dr. Thaler and the Navy found themselves fighting a new kind of war, the Radio Cold War. Diplomatically, nations, allied and neutral alike, began lodging formal complaints with the International Telecommunication Union, ITU. Broadcasters from Europe to Asia complained that their signals were being obliterated by a sweeping, rhythmic noise of unknown origin, often referred to colloquially by radio operators as the woodpecker effect, though Thaler's early system was more of a constant, disruptive roar than a rhythmic tapping. The irony was profound. The U.S. was using the very airwaves relied upon by the world to secure its survival, but in doing so, it was causing a global headache. The military could not simply turn the power down. Reducing the transmission power meant sacrificing the long-range signal integrity necessary to detect the faint echo of a missile plume thousands of miles away. They were forced to maintain the high wattage, despite the international outcry. Thaler's team was tasked not with eliminating the interference, which was structurally necessary, but with making it less disruptive and less detectable by hostile nations. The goal was to refine the signal structure to be less polluting while maintaining the required radar energy on target. This led to the next major technical leap, moving from a constant, high-power continuous wave (CW) transmission to a sophisticated frequency-modulated continuous wave (FMCW) signal, often combined with complex, high-duty cycle pulse trains. Instead of simply blasting a constant tone, the ODH system began transmitting highly complex, tailored waveforms that were designed to compress the necessary energy into brief, highly efficient bursts. The new signal architecture was mathematically brilliant. It utilized chirp waveforms, signals whose frequency increased or decreased linearly over time, to maximize the effective energy hitting the target while reducing the total time the signal occupied any single, narrow radio channel. This allowed the system to quickly hop across a wide bandwidth, minimizing interference to any one specific broadcasting station. The noise was still present, but it was now a fleeting, hard-to-pin-down ghost instead of a perpetual giant. Furthermore, the sophisticated nature of the FMCW and pulse waveforms made it extremely difficult for the Soviet Union to analyze the signal and reverse engineer the radar's operational parameters. The Soviets could hear the signal, but they could not easily discern the coded information being sent or, crucially, the precise time delay measurements being used for range calculation. The woodpecker had to be an invisible bird. Thaler's team also implemented a more aggressive form of adaptive frequency management. The Guardian computer was programmed to monitor local and international frequency allocations, identifying and avoiding critical channels used for aviation, maritime distress, and essential diplomatic communication, an ethical, if not strategic, necessity. The radar would intelligently tune around protected frequencies, ensuring that the necessary function of the system did not completely paralyze global communication. However, the international and amateur radio communities continued to track the massive transmissions. The very existence of this overwhelming, high-power noise, shifting across the HF spectrum and seemingly originating from massive antenna farms, was itself a major intelligence indicator. The Soviets, masters of signals intelligence, were certainly aware that the U.S. had deployed a radical new form of detection. They just didn't know exactly how effective it was or how to counter it. The deployment of the advanced, low-interference waveform solidified the ODH radar as a permanent, viable technology. It proved that Dr. Thaler's system was not a temporary patch, but a dynamic, adaptable tool capable of evolving its tactics to meet both the physics of the ionosphere and the complexities of the geopolitical landscape. The stage was set for the final, massive expansion of the OTH network, the creation of a globe-spanning fence to enclose the Soviet threat. With the technical and diplomatic hurdles somewhat managed, the interference minimized, and the system's effectiveness undeniable, the U.S. military committed fully to the over-the-horizon radar concept. The era of the single, experimental station in Maine was over. Dr. Thaler and his team were commissioned to design and oversee the deployment of a continent-spanning network, a continuous, electronic radar fence designed to provide 24/7 multi-layered coverage across the entire strategic threat perimeter. This vast undertaking was formalized under a high-priority Department of Defense program, leading to the development of the first fully integrated operational OTHB, over-the-horizon backscatter systems. The term backscatter was the key. It described the process of the signal bouncing back toward the originating site after reflecting off the target in the ionosphere, a process that Thaler had pioneered. The plan called for the construction of multiple, geographically dispersed ODH complexes. The initial focus remained on the eastern seaboard to maintain continuous surveillance over the Soviet launch zones in Eurasia. A second, equally massive complex was slated for the western United States, aimed squarely at potential threats originating from the Pacific Rim, including Soviet naval forces and possible future ICBM tests from their Far Eastern launch sites. Each complex was an engineering undertaking on the scale of a major defense base. The design of these new sites incorporated all the lessons learned from the experimental phase. They featured dedicated, geographically separated transmit, TX, and receive, RX sites, often hundreds of miles apart. This bistatic configuration was crucial. By separating the transmitter and receiver, Thaler's team could significantly improve the signal-to-noise ratio. The massive transmitted energy would never overwhelm the highly sensitive receiver antennas, which are designed to listen for the faintest, nanoscopic return echo. The TX sites were home to the immense power generators and the vast linear antenna arrays, which could stretch up to a mile in length, beaming their multi-megawatt signals low over the horizon. The RX sites, by contrast, were quiet, isolated sanctuaries for the receiving arrays, which were often even longer than the transmitters, sometimes 2 or 3 miles long, to maximize the collection aperture and enhance directional accuracy. This separation meant the ODH system was not a single point, but a system of systems, a geographically distributed organism of detection. A crucial development for the new network was the integration of sophisticated frequency management centers. These centralized nodes receive continuous data from all remote ionospheric sounding sites, both dedicated probes and data gathered from the operational radar's own reflections, to create a unified, predictive model of the global ionosphere. The Guardian computer successor could now not only adapt its frequency, but could also predict, with hours of advance notice, the best operational frequencies and beam steering angles for each site, ensuring coverage was rarely lost due to solar or seasonal shifts. Thaler and his lead engineers also tackled the issue of multiple skip paths. HF waves could bounce off the ionosphere not once, but twice or even 3 times, greatly extending the theoretical range. However, this created ambiguity. Was a return from 6,000 miles a single skip echo, or a weaker, double skip echo from 3,000 miles? New algorithms were developed to analyze the attenuation and time delay differences between the competing return paths, allowing the computer to correctly assign the return to the correct skip zone. This precision was vital for accurate launch location and trajectory determination. By the mid-1960s, the American ODH radar fence was taking shape. It was a silent, sprawling monument to the unexpected application of high-frequency radio physics, constantly probing the atmosphere and effectively extending the U.S. frontier thousands of miles into the enemy's backyard. The initial crazy radar trick had evolved into a fully networked, strategically indispensable component of a nation's defense triad, operating in perpetual secrecy, watching the globe's curve. Its quiet, relentless vigilance was the first line of defense against the ultimate threat. Type continue to generate the next section. The next section should focus on the impact of the ODH system on the Soviet Union and how its success led to a new, desperate attempt by the Soviets to counter or mimic the technology. This begins the technological counter-response phase of a narrative. Previous _section _text. By the mid-1960s, the American ODH radar fence was taking shape. It was a silent, sprawling monument to the unexpected application of high-frequency radio physics, constantly probing the atmosphere and effectively extending the U.S. frontier thousands of miles into the enemy's backyard. The initial crazy radar trick had evolved into a fully networked, strategically indispensable component of a nation's defense triad, operating in perpetual secrecy, watching the globe's curve. Its quiet, relentless vigilance was the first line of defense against the ultimate threat. The presence of the American ODH radar, even under the cover of immense secrecy and complex signaling, did not go unnoticed in the Soviet Union. Their sophisticated signals intelligence, SIGINT, facilities were fully aware of the massive, sweeping HF transmissions originating from the American coasts. The frequency, agility, and sheer power suggested a new, highly effective form of wide-area surveillance. Soviet engineers and military strategists quickly deduced that the U.S. had found a way to reliably exploit the ionosphere for detection, overcoming the traditional line-of-sight limitations. The strategic nightmare for the Kremlin was immediate. If the Americans could see a launch from Tyuratam, their critical window of surprise was eliminated. The Soviet response, predictably, was a massive, accelerated commitment to not only counter the American ODH radar, but to replicate and expand upon the technology themselves. The Soviet equivalent of Project Teepee was born, and it was engineered with characteristic Soviet brute force and disregard for environmental or international consequences. Led by Dr. Franz Kuzmin, a parallel figure to Thaler, the program was aimed at creating an ODH system that could peer over the North Pole and deep into the continental United States, neutralizing the warning advantage Thaler had created. The result was the construction of the infamous Duga array. If the American ODH sites were vast, Duga was colossal, a terrifying testament to unchecked technological ambition. Built in the remote Ukrainian SSR and later a second site in the Russian Far East, the Duga antennas were staggering, a monolithic wall of steel girders and wires stretching for miles, towering over 150 meters high. It looked less like a radar and more like a ruined city built for giants. Unlike the American system, which struggled for years to minimize interference, the Soviet Duga system was initially deployed with raw power as its priority. When Duga was first activated in the mid-1970s, it completely disregarded all existing international frequency allocations. It transmitted with an estimated 10 megawatts or more of raw, continuous pulse energy, far exceeding the power and frequency discipline of the American ODH. The interference was immediate and global. The woodpecker nickname, originally a slight exaggeration for the American system, now accurately described the Soviet Duga's sound, a relentless, sharp, machine gun-like tapping noise that hammered the short wave bands 24 hours a day. It was so loud and so pervasive that it became a major diplomatic incident, disrupting aviation's safety frequencies, jamming ship-to-shore communications worldwide, and infuriating millions of international radio enthusiasts and legitimate users. Duga's relentless signal became the most powerful and widely discussed man-made radio signal on the planet. The technological goal of Duga was the same as Thaler's, to detect the launch of U.S. ICBMs, particularly from silos and submarines. However, its sheer, unchecked power was also an intentional act of electronic warfare. By overwhelming the HF spectrum, the Soviets were essentially flooding the operational bands, forcing the American ODH systems to fight harder to isolate their own returning echoes. The Russian woodpecker was a massive act of radio jamming against the global communication system, and indirectly against Thaler's careful, adaptive ODH network. Thaler's teams in Maine and the West Coast had to rapidly update their algorithms to cope with the sudden, powerful onslaught of Duga's signal. The challenge was no longer natural noise, but a deliberate, hostile, megawatt-level interference source that often landed directly in their optimal receiving windows. The Cold War had escalated from strategic competition over missiles to a battle over radio waveforms and spectral dominance. Thaler's civilian-led ingenuity now found itself in a head-to-head electronic duel with the full, unrefined power of the Soviet state. Type continue to generate the next section. The next section must focus on the American ODH response to the Soviet Duga interference. This means detailing the advanced filtering, digital signal processing, and specialized techniques Thaler's team developed to see through or filter out the powerful Duga signal. This is a technical countermove in the electronic duel. Previous_section_text. Thaler's teams in Maine and the West Coast had to rapidly update their algorithms to cope with the sudden, powerful onslaught of Duga's signal. The challenge was no longer natural noise, but a deliberate, hostile, megawatt-level interference source that often landed directly in their optimal receiving windows. The Cold War had escalated from a strategic competition over missiles to a battle over radio waveforms and spectral dominance. Thaler's civilian-led ingenuity now found itself in a head-to-head electronic duel with the full, unrefined power of the Soviet state. The sudden, brutal electronic assault launched by the Soviet Dugas system presented the most severe challenge Project TP's successor network had ever faced. The American ODH radar was designed to filter the gentle noise of the natural world. It was not designed to contend with a deliberate, high-power, hostile transmission that could instantaneously obliterate the faint return echoes of a missile plume. The Soviet woodpecker was, in essence, trying to blind Thaler's ODH fence by turning the global shortwave spectrum into a chaotic static battlefield. Dr. Thaler recognized that brute force could not defeat brute force. The U.S. could not simply increase its own power output to drown out Duga without violating its own self-imposed constraints on frequency management and international law, and risking escalating the interference into a globally crippling electronic war. The solution had to be one of algorithmic superiority. Thaler tasked his computer and signal processing specialists with a singular goal: devise a mathematical technique to see through the Dugas signal, effectively turning the massive Soviet transmission into a known, predictable form of noise that could be instantly subtracted from the incoming data stream. This challenge ushered in the age of sophisticated digital signal processing, DSP, for OTH radar. Previously, filtering relied on analog components and simpler computational models. Now, the Guardian's successors, vast, modern mainframe computers, were dedicated to running complex fast Fourier transform, FFT, analysis on the raw receiving data in real time. The key breakthrough came from analyzing the very structure of the Duga signal. Although immensely powerful, the Duga transmission had a highly regular, repetitive tapping rhythm. The signal's frequency, pulse width, and repetition rate were fixed. This regularity was Duga's greatest weakness. Thaler's team developed a technique called adaptive notch filtering and coherent integration. They programmed the ODH system to precisely characterize the Dugas signature, its exact frequency, pulse timing, and amplitude. Once characterized, the system created a mathematically inverse or negative copy of that noise. It would then dynamically inject this anti-signal into the received data stream, effectively canceling out the Soviet interference upon reception, leaving behind only the fainter, non-repeating signals, including the critical Doppler-shifted echo of an ICBM. It was like tuning a piano to play an anti-note that would silence the original note, or using a computer to recognize a specific watermark on a noisy photograph and mathematically erase only the watermark, leaving the image intact. The process had to occur at the speed of light, ensuring that the necessary cancellation was performed before the ICBM echo could be lost forever in the overwhelming noise. Furthermore, they optimized their own FMCW chirps to exploit Duga's fixed rhythm. They could time their own transmissions and receiving windows to fall precisely during the tiny, momentary gaps between the Duga pulses, a process known as time-sharing or interleave processing. This reduced the overall impact of Duga's transmission, giving the American system clean windows in which to listen for returns. The results were stunning. Within months of Duga's operational deployment, the U.S. ODH fence was able to track targets with nearly the same fidelity as before the Soviet interference began. The computer was successfully isolating the unique, non-repeating Doppler signature of a speeding missile plume from the rhythmic, high-power static of the Soviet woodpecker. The electronic duel had been won not by power, but by precision and ingenuity. This constant, high-stakes duel between Thaler's technology and its Soviet counterpart drove the ODH radar's rapid evolution, pushing the limits of DSP and adaptive computing. The system wasn't just a powerful radio. It was a highly intelligent electronic filter designed to extract strategic truth from a battlefield of chaotic noise, a lasting testament to the genius of William Thaler's foundational idea. By the late 1970s and early 1980s, the over-the-horizon radar network, refined by the constant challenge of the Soviet Duga system and decades of ionospheric modeling, had transcended its experimental origins. It was no longer just a project. It was a fully integrated, operational component of the North American Aerospace Defense Command, NORAD, the core of the continent's strategic warning infrastructure. The OTH fence, with its vast antenna arrays stretching across multiple U.S. coasts, provided a continuous, 180-degree sweep of the planet, thousands of miles beyond the limits of conventional ground radar. The system proved to be an exceptionally reliable asset, fulfilling the promise Thaler had made in the Pentagon conference room years before, providing tactical warning measured in hours, not minutes. Its primary role remained the detection of ICBM launches from the Soviet Union, but the system's capabilities expanded dramatically. Due to its long-range, wide-area surveillance, the ODH radar was uniquely suited for detecting cruise missiles and strategic bombers approaching the U.S. coastlines at low altitude, targets that could often slip beneath the pencil-thin beams of conventional microwave radar. Because the ODH signal utilized the atmospheric skip to look down onto the surface, it could see low-flying aircraft that were invisible to ground-based line-of-sight radar, extending the warning perimeter hundreds of miles out to sea. Furthermore, the system became invaluable for maritime surveillance. The faint Doppler returns from ships and large aircraft far out over the ocean provided crucial intelligence on the positioning of Soviet naval assets, particularly ballistic missile submarines, SSBNs, that represented a terrifying first-strike threat. The ODH radar was now serving the Navy, Air Force, and intelligence community simultaneously, all thanks to Thaler's unorthodox use of simple shortwave radio. William Thaler, the visionary physicist, saw his foundational concept codified into a permanent national asset. He had successfully argued for, designed, and proven a system that relied on the very phenomenon, atmospheric noise and ionospheric fluctuation, that generations of radar engineers had tried to defeat. He had taken the greatest environmental weakness of radio waves and turned it into the greatest strategic strength. The system's intelligence was now so advanced that it could often distinguish between different types of launches based purely on the Doppler signature and acceleration profile. A small, single-stage tactical rocket had a different sound than a massive three-stage ICBM. The ODH computer was an electronic savant, identifying threats by their characteristic acoustic fingerprint, filtered out of the cacophony of global radio noise and the deliberate electronic jamming of the woodpecker. The ultimate measure of the ODH radar's success, however, was in the effect it had on the Cold War itself. By eliminating the element of surprise from a potential ICBM attack, it introduced an essential degree of stability to the strategic balance. The Soviets knew that any launch they made would be observed almost immediately. This knowledge, combined with the U.S.'s ability to retaliate, contributed significantly to the doctrine of mutually assured destruction, MAD, ironically making the world safer by ensuring no nation could secretly launch a devastating first strike. The quiet hum of the massive antenna arrays along the American coasts was the true, unsung sound of deterrence. The civilians' crazy trick, born out of the post-Sputnik panic, had become the invisible shield of a superpower, extending American eyes over the curve of the Earth and securing the long-term strategic advantage that the U.S. so desperately needed. As the Cold War drew to a close in the late 1980s and early 1990s, the strategic landscape that had necessitated the over-the-horizon radar began to shift. The Soviet Union disintegrated, and the direct, existential threat of a massive ICBM barrage across the North Pole diminished. With the advent of increasingly capable and cost-effective DSP infrared surveillance satellites, the ODH radar's primary role as the sole extended-range missile warning system began to wane. The massive, electricity-hungry, and environmentally contentious ODHB sites, with their miles-long antenna arrays, became subject to budget scrutiny. While still highly effective, the expense of maintaining the megawatt-level transmitters, the vast cooling systems, and the teams of highly specialized technicians required to manage the ionospheric complexities was increasingly difficult to justify in the new geopolitical climate. The military began a phased decommissioning of some of the original, massive OEHB complexes. However, the technological legacy of Dr. William Thaler's work did not vanish. Instead, the concepts he pioneered became foundational to almost all subsequent wide-area surveillance technology. His team's innovations in adaptive signal processing, the mathematical techniques used to filter atmospheric noise, compensate for ionospheric fluctuations, and see through the hostile Douglas signal, became essential elements of modern defense electronics. Every piece of sophisticated radar technology today, from anti-missile defense systems to advanced airborne surveillance platforms, incorporates Thaler's lessons. The use of complex, frequency-agile waveforms, like the FMCW chirps, and a reliance on high-speed digital signal processing to extract faint targets from heavy clutter. The idea of a radar system that listens to its environment and intelligently adapts its operational frequency based on real-time atmospheric data is now standard practice, a direct evolution of the ionospheric sounding techniques developed for Project TP. Furthermore, the ODH concept found a lasting home in areas beyond ICBM detection. Australia, with its vast maritime borders, recognized the enduring value of Thaler's technique and deployed the massive Jindalee Operational Radar Network, JORN, to provide low-cost, wide-area surveillance across its northern and western approaches. JORN's core principle is identical to Thaler's original vision, using ionospheric scatter to track aircraft, ships, and drug runners thousands of miles from the Australian mainland. The technology proved particularly adept at border security and counter-drug operations, utilizing the same long-range maritime tracking capability originally designed to find Soviet submarines. The OTH radar, once the ultimate tool of nuclear deterrence, found a new life as a mundane but highly effective law enforcement and border protection asset, covering areas that satellites could not economically monitor continuously. Dr. William J. Thaler himself stepped away from the direct management of the military programs, his unconventional brilliance having achieved its ultimate goal. He had solved the most pressing physics problem of the early Cold War, how to see over the curve of the Earth, by convincing the world to embrace the very noise it was trying to eliminate. His initial crazy radar trick had not only created a massive, effective defense system, but had permanently reshaped the field of radar and radio science, proving that sometimes the most revolutionary solutions are found not in conquering nature, but in exploiting its quirks. The story of the over-the-horizon radar is not just a footnote in the history of Cold War defense. It is a profound testament to how a single, unorthodox idea can shatter technological limitations and fundamentally alter the course of geopolitical strategy. For years, the curvature of the Earth was the Soviet Union's most effective strategic shield, guaranteeing them the element of surprise. William Thaler, the civilian physicist, saw that natural barrier not as an obstacle to be overcome by sheer height and power, but as a natural lens to be exploited by ingenuity. He didn't demand new, theoretical physics. He simply applied old, discarded radio physics, the familiar phenomenon of short-wave skip, to a new, terrifying problem. He took the ionosphere, a chaotic, solar-driven layer of atmospheric noise, and mathematically tamed it, turning it into the most critical element of the American early warning system. The OTH radar network, with its silent, mile-long antenna arrays and its megawatts of sweeping power, was the bridge that kept America safe during the most dangerous decades of the nuclear age. It was the crucial gap filler between the primitive warning systems of the 1950s and the reliable satellite networks of the 1980s and beyond. Without the ODH fence, the U.S. would have operated under a constant, paralyzing pressure, knowing that a successful, surprise ICBM launch would leave them with only a few minutes to decide the fate of the world. Thaler's system bought time. It bought hours of warning, time for leaders to think, time for forces to react, and time for diplomacy to potentially intervene. That expansion of the decision window was, arguably, one of the most significant non-lethal contributions to maintaining the fragile global peace during the Cold War. Today, While the giant, original ODH installations may be slowly disappearing, the principles they championed, adaptive frequency management, digital clutter rejection, and the brilliant simplicity of using an environmental quirk for advantage, remain central to modern surveillance. Every time a contemporary military radar system dynamically shifts its frequency to avoid interference or deploys a complex, coded waveform to hunt a faint target, it is echoing the genius of Project Teepee. The ultimate lesson of the over-the-horizon radar is that the greatest technological victories are often found not in building something entirely new, but in looking at something familiar, like the radio waves that bounce off the sky, and seeing its hidden, revolutionary potential. William Thaler didn't build a better missile detector. He built a mirror in the sky, allowing a nation to finally see its own fate reflected from thousands of miles away.